I'm going to introduce our first speaker, Peter Welinder, who is my coworker on the robotics team at OpenAI, where he's kind of pushed a lot of our vision work forward, and has generally been involved in pretty much every part of the results that we've had there. Peter joined OpenAI from Dropbox, where which he joined after selling his startup to Dropbox, and went on to lead machine learning there. So really excited to welcome Peter. Thank you.
Thank you, Josh, and thanks for having me. Cool. Yeah. So Josh asked me to talk about more tooling and stuff like that, and instead I decided to talk about something slightly different, which is how do you actually kind of make progress on hard research problems? Because I think this is something that if you're working on AI, this is something you will all have to face, because it's one of those things where most of AI stuff is kind of at the forefront, and you need to put together a lot of pieces that might not be completely working, and you need to do a lot of experiments to actually get things working together. And in some ways it's similar to engineering, in some ways it's not. And if you're more often than not, you're going to be working with a team of people to accomplish things. And so how to think about this, how do you kind of make progress as a team to solve really hard machine learning kind of on the edge of research problems? There are kind of some things that I've learned throughout my career kind of that are useful for this. So as Josh said, like, just to give you a little bit of context, my background is kind of 10 years ago, I was in grad school, so I was doing research there, and then I did a startup for a while, and which is very different from doing graduate school research. Then at Dropbox, again, very different, where suddenly from a startup you have very little time and very little resources. You have much more resources, and you can actually try to solve much harder research problems. And now at OpenAI, where it's like we're really trying to solve things that nobody has ever done before, which is really which we have no idea whether we can even solve. And the interesting thing is that there's a lot of kind of similarities between these things, and kind of some kind of common patterns of how you can actually make progress on hard problems. So that's what I will talk about here. And if you have questions along the way, you should just interject, because I want this to be somewhat interactive. So before I kind of talk about those general ideas, give you a bit more context on what I'm working on right now on, and it's at OpenAI. As Josh said, I'm working on robotics. We're trying to build a general purpose robot. What that means is a robot that can kind of do most things that humans can do. So that would mean things like things like I don't know, cracking eggs, or building things, putting together furniture. These are all things that robots can't do today, but we feel like we're not so far away from making that happen. And the key kind of thing that we're missing is being able to learn how to do these things, like having the robot actually learn how to do these things. Today, robots are pretty much pre-programmed to do most things, and the big missing component is learning. The ingredients that we are using at OpenAI is kind of they're really like three big ones, and the obvious one is deep learning. It's just like an extremely effective tool to solve most machine learning problems today. That wasn't at all the case 10 years ago, but now it seems to work for almost anything you throw at it, as long as you have enough data and enough compute. The other thing that's, this is so successful, it's obviously used in businesses and industry and so on. The thing that's not very used in business settings yet is reinforcement learning. So what you see here is like, this is the OpenAI Dota 2 bot. I think this is a 1 versus 1 setting where it's actually the computer who's making some of the choices here, I think. And what we use here is reinforcement learning. How many here know about reinforcement learning? Okay, so maybe half of you. So reinforcement learning is kind of somewhat different than supervised learning, in the sense that instead of getting both labels of the data, you're also getting instead of those labels, you're getting a reward signal. So you have usually the setting is you have some agent moving around in some environment. It does some actions, it gets observations back, but it also gets some reward signal. And it turns out this is a really, really powerful paradigm for training kind of more open-ended agents. And so you can train robots to do very interesting things. You can also train things in computer games. The last thing is scale. Scale is really what kind of makes things work, especially for reinforcement learning. And at OpenAI, we try to kind of be, 5 to 10 years ahead of the rest of most of the world in terms of having compute available to do these things. And the idea is that, in 5 years, most of the world will be there. So then these things will be very useful. And it also lets you kind of, be more honest in the kind of experiments you're running, because you can kind of use simple tricks and get pretty far. So these three ingredients are kind of the primary ones we're using for a lot of our research.
What does compute 5 years ahead look like?
I think the way to think about it is like, if you're training models right now, a lot of times, like say a computer vision model, deep learning model, you might be using kind of two GPUs, sometimes 4, and we would use like 400 or a few thousand, like that. So it's really just like 2 or 3 orders of magnitude more than you would have in most setups. Yes.
Do you think in like 5 to 10 years, like 2 to 4 GPU might be equivalent in performance to 500 now? Is that the thinking, or
yes,
our ability to distribute would be that much more?
I think it's a little bit of both. Like, I think it will be easier for everyone to have more distributed jobs. Like, it will be cheaper. So we actually, this is like a kind of pretty big research topic, even at this one at OpenAI, trying to figure out where will we be in terms of compute in a couple of years. We have a really good blog post about this. And what it looks like right now is that compared to Moore's law, which is like, compute doubling every 18 months, right now for deep learning applications, for like solving hard problems, it seems to be every 4 months. So that means like 10x approximately every year, and it looks like we will have that for the next 3 to 5 years. And so it will. The only thing that's that's making it hard to use now is like costs a lot of money, and the infrastructure is not there. But prices will go down, and infrastructure is easy to eventually copy. So it will happen. Here's an example of what we can do now. Let's see. So this is our robots. This is a result from last year. And what is happening here is that the robot is trying to reorient this cube into different orientations. The goal orientations is here on the lower right. So whenever it achieves a particular goal, we sample randomly a new goal. And so this is like an example of like using reinforcement learning to try to kind of solve a very hard problem in terms of robotic manipulation, trying to like control a robot with a lot of degrees of freedoms here, like there's lots of joints in the fingers and so on, is a really, really hard problem. And so reinforcement learning is a good way of approaching it. Yes?
Just what if you give it an impossible configuration? Does it realize eventually it will realize it's impossible, or it will keep just going through?
Well, I guess here it's really hard to give it like an impossible configuration, just because like it's only rotating this cube in any.
You could just put the letters such that the configuration doesn't exist on this cube.
Oh, I see. Yeah, in that case, I mean, it is not that general. Okay. For a lot of these things, they're like, this is like the hardest problem right now in machine learning, is like making things really, really general. Yeah. Right now, we're trying to get like the not very general, like things that are easy for humans to work, when we can't even get those to work. Yeah. But the next thing would be what you said. That would be really cool.
What's the level of generalization that this robot has?
So the level of generalization is like, you could probably like put in slightly bigger or smaller cubes. We put in like blocks that are like squishy, like stress balls and stuff like that. Different shapes of objects, heavier, lighter, and stuff like that. It can deal with. Also, if the hand here is slightly broken, it will still work and so on. So there's some generality to it, but like nothing at all compared to human.
So the image part of it is kind of irrelevant for this purpose. Is that right? So like different colors or
that is very specific. There's no generality really for that. Like here is like we're training it. I mean, maybe you can make a slightly different hue of yellow or something like that. But this is the way to think about it is kind of showing that it's at all possible to do something like this. Very much what our research director at right now is actually to try to make it much more general, like putting in any object in that hand, or eventually like using any robotic hand and so on. Like that's kind of where we're going to want to get to. But right now, that's not at all the case of the setup.
Just maybe what this question was. So in this view, if let's say the letters were not there, would it still be able to do it, like just based on colors or no? I guess that's the question as I understand.
Maybe. I think in this case, it might be using the letters quite a lot. Like we have trained a model with those letters. And as you might know, like these neural networks are really lock onto the data distribution, and they're not good at generalizing out. Like sometimes they can, but often they cannot.
And are these models fine-tunable, like vision and language models?
These are actually trained from scratch.
Right, but like given that it learns this now, how difficult would it be to say train it to open a bottle cap on top of this?
Right now, very hard.
Okay. So it's as if you had to do that whole task again.
More or
There's
less,
no
yeah.
advantage of having this. Okay.
Exactly, and that's kind of where we want to get to, is things that are much more general like that. You had a question?
Is the choice of the humanoid form of the hand intentional?
Yeah, well, so the story behind that is pretty interesting. Like, kind of, we went to a number of robotics conferences, and like when we started working on this project, like a lot of us actually did not have a lot of experience in robotics. We had much more experience in machine learning and deep learning and reinforcement learning and stuff like that. So we asked people at these conferences, so what is the hardest problem in robotics? And everybody said, well, the problem I'm working on is really, really hard. So, that wasn't super helpful. But if you kept on pushing, like what kind of came up was robots that have a lot of degrees of freedom, that is a lot of joints, are really hard to control. The other thing that's really hard is interacting with objects, because a lot of way robotics is done today is like you need to have really accurate models of everything. And so it's really hard to have good models of all kinds of objects. So we picked the robotic hand because it was one of the robots that had the most degrees of freedom. And like and obviously there was some foresight here also in if we can control that, then presumably there's a lot of interesting human tasks that a human can do that we can tackle using this system, because we can do it with our hands. We should be able to do it with a robotic hand.
Isn't that a reinforcement learning problem as well, where you say what's the best design? Genetically, we solve it to be this design.
Yeah.
But there could be a better design.
Yeah. I think you're right. Like you could do that as well. What is interesting here is like sometimes you see that it doesn't use like this finger very much, for example. So it could have gotten away with 4 fingers instead, probably. The interesting thing is that this hand is somewhat different from a human hand, and it kind of does some moves that are different than a human would do. For example, it has a much more flexible thumb. It's like can do really weird movements. It kind of hurts in your hand when you look at it a little bit. But it's been really interesting because, like, again, all of this is actually trained from scratch. Like, we have not told it how to do these movements at all. And some of them are very human-like, just because it got a human-like hand. Yes?
Do you train this in the physical world or in a simulation?
Entirely in a simulation. And this is like the first time it's running on a real robot.
Oh, wow. So the simulation it has to be perfectly matching the design.
So this is it's a very good question, and the trick is actually, and this was something that Josh actually came out of his research, is the way you train this is you train it in simulations, lots of simulations with that all have different parameters of physics. Like some would have really strong gravity, some would have light gravity, some will have a very heavy object in the hand, and some will have a very light object in the hand, and so on. And if you do that, if you train in enough diverse environments, it turns out that you can transfer to the real world. Cool. So anyway, this is what we have done so far. And so I wanted to think about then how do you kind of deliver really good research results, and specifically how you do it as a team. Because I think this is really important, because it's really hard to especially in AI research today, to kind of make breakthroughs or even put things together and get them to work as a single person. You need to really need to think about it as a team, because the problems are just so hard and there's so many components. And so I was thinking of like some things we've learned at OpenAI and at other kind of projects I've been doing at Dropbox and before that. But to kind of put it a little bit more in context, like the projects we are doing at OpenAI is kind of, most projects are on the order of a year in length, and we have 5 to 15 people working on them. So they're pretty big projects, and we try to kind of get to a really hard research, solve a really hard research problem during that time with such a team. And again, like I feel like there's a lot of kind of interesting parallels between research and engineering, but also some differences. Like so we really need to think about like what can we learn from engineering and apply it to research to make progress on research, but what is also different so we can think about research in the appropriate way. Okay, so there will be, I will talk about 5 lessons basically. And one of the first one is hypothesis over tasks, meaning you have to start thinking about, when you're doing engineering, you can think about a lot of things in tasks. But when you're doing research, you have to start thinking in hypotheses. To give you kind of an example, like a really good analogy, I think, for building things with engineering is you can think about it as building kind of a block tower. For example, if you're building a camera app, you need to kind of think about what are the components that make up my camera app. I need some camera UI. I need to be able to save photos. I need some server backend that can potentially sync these. I need to think about the APIs, and all these are like different components. And you know that you will be able to build a camera app and if you think about it hard enough, you can figure out what all the components are. So you know how to kind of parallelize that work across multiple people, how to create the right interfaces and put them all together. And you can have some confidence in those, and you can usually estimate pretty well on how long it will actually take to build this thing. Like, estimating how long engineering problems are hard, but you can often do it within a factor of 2. With research, it's much harder. I think this coming from XKCD, it really captures this really, really well. I'm sure a lot of you have seen this, but let me read it. It's weird to read a comic, but I will do it anyway. So when a user takes a photo, the app should show whether in a national park. Sure, give me a GIS to look up and give me a few hours. And then you should check whether the photo has a bird. Well, for that, I need a research team in 5 years. And this is really the core issue. Like, because if you're doing research, you're really operating in this realm of the virtually impossible. And you're really trying to push the limits, and you don't know how long things will take. So you kind of, there's no way to get around this. You kind of need to embrace it and embrace that for your working style in order to be productive. So going back to like the block analogy, it just doesn't work anymore. You don't know all the components beforehand. Then it would be an engineering problem. It would not be a research problem. So you kind of need a better framework for thinking about that. And I think an analogy that works much better is kind of thinking about that there is this kind of mountain you want to get to, and you can see this peak, and you want to reach this peak and feel kind of really glorious when you get there, and you will understand the world in a different way. But between you and that peak, there's all these obstacles. There's a big forest. There's potentially dangers and pitfalls along the way, but you need to get there. So how do you do it? Here it looks very easy, just go in between the trees and you can get to the peak. But really, it looks more like this. Like, you can't really see that far ahead. there's like big, thick vegetation, and you kind of have to make a call on what you're going to do just in the short term. And the way you think about it is like there are a few hypotheses. You usually have like on the order of like anywhere from 2 to 5 different things you could be doing to learn a little bit more about the problem. And that is the key. Kind of they're kind of short-term tasks, but they're very explicit hypotheses. Now, excuse me, if you actually reach the peak, then your path will look something like this. You will have tried a lot of things that didn't work out. And often when you think about research, it's like 90% of the things you do don't work out. And you kind of have to accept that. And that's kind of part of the process of finding the way. And again, so if you think about it in this very explicitly, where in engineering you have concrete tasks, in research you have hypothesis, then you can start thinking a little bit more about like how do you tackle this and how do you measure your progress? Well, one way to measure your progress is like just how many hypotheses can you try? And if you're more people, you can try more hypotheses. And the fact is also that you might need to try all 4 hypotheses, or you might need to try 1 hypothesis to kind of get to the next stage. So you maybe here you try 2 of them, and then you don't even need to try 3 and 4 because whatever you have is good enough for the next step. And then you get a new set of hypotheses, and that's kind of the way you need to operate. And the really beautiful thing about this is if you're a team, the way to make progress is really to very clearly identify these hypotheses and then make progress as a team, split up the work and do it, and then make progress as a team. And just accepting the fact that 90% of the team will be working on things that doesn't work out. But that's fine because what you're making progress is as a team and not as the individuals. And this can be very powerful because then then you don't feel as bad when your things don't work out. You kind of just have to accept it, and instead you can be more happy when your coworkers' thing works out, and the next time it will be your thing that works out. But nobody really knows beforehand, and that's kind of just the way that it is. Now, yeah.
How do you handle the shifting from the 1 to 3 to ABC? Means if I was assigned to 3 and 4. Just stopping that and asking me what I see now.
You need to get really good at just abandoning your code and stuff like that. Like have no emotions to the things you have created, because it's like it doesn't matter in the end, and so that's usually how it works. To be quite honest, like it's very often at OpenAI we do this. We work on things, and then like one thing works out, and then it's like all these other things we're working on. It doesn't matter anymore. We just drop it because now we have something much better to build upon, which we can move forward with.
And then do you have a notion of matching how much I believe in hypothesis with me actually working on hypothesis?
Yeah, so this is a good point. Like, I think you can prioritize the hypothesis like a little bit based on like your prior on how well they work, and after that it is a little bit. It's similar to like any task management in some sense. Like some people will have better skills to do certain things. Some people will be more motivated to do certain things. So you can use pretty standard principles to kind of figure out who does what. But I do think the thing that's related to what you said is that not all hypotheses might be equal. You might have some that you believe in more as a team as well.
Did you have to like sometimes backtrack on your hypothesis progress? Like you got to like almost level 3 and then got a dead end, so you can go all the way
back? Yeah. Sometimes it happens. Like you can hit walls. I think that's happened to us sometimes. More often than not, you learn other things along the way. Like you kind of unlock other paths that might be earlier from just discoveries you make and so on. But it does happen. You can put a lot of effort into one direction, and you just have to backtrack and take a completely different approach because the approach you took was just the wrong one. And that's also part of research.
So you mentioned backtracking. So how far and how do you actually keep track of where to go back to?
Okay, I will talk more about that later. Actually, that's a good question. So now the second lesson I want to talk about is metrics, because I think this is something that's a little bit neglected in doing research, and I think it's extremely important for team-based research. As a community, at least a lot of machine learning, big piece of the machine learning community is relatively good at this. This is a way to kind of, in the computer vision community, for example, everybody there's a number of data sets and people make progress on those data sets. There are some shared metrics and so that's the way you move forward as a community. But I would argue this is extremely important for teams, because it works a little bit like a compass. It kind of gives you a sense of, are you going in the right direction? The first thing you need to do in order to pick a good metric is to kind of, you need to think about the global problem. And if you're a company, that might be, how do I want to achieve $100 million revenue, or 1 million users, or $1 billion valuation. At OpenAI, we want to build safe AGI, which is artificial general intelligence. But those are really hard things to think about. So you kind of need to create something that's a little bit more tractable. So for robotics team at OpenAI, we think that general purpose robot is a path towards safe AGI. But even that is pretty big thing. So then the simplest thing to work on in the short term seems to be, well, can we get a robot even to rotate the thing in the sand? Pretty far away from a general purpose robot, but it's something much more concrete. And you kind of want to pick something very, very concrete, and then you want to kind of pick your a data set that's related to that. And the data set and the metric is extremely important. Like spending the time to, say, clean up a data set and like make it so that you really trust your data set is always worth the time. Because the worst thing is like if you spend months on things and then you realize there's like bugs in your data set, in your evaluation code, or like things have been mislabeled and so on. That really sucks, because you've basically wasted all your work. So getting that very, very clear is super important. And then picking the metrics that you want to optimize as a team. Here's just one example. I won't say exactly what metric it is, but it's a real metric that we were tracking for the past few weeks at OpenAI. And so we started out like at about 30% error, and then we have maybe 3 or 4 people working in parallel on different hypotheses. And every week we make progress as a team to reduce this error rate. It's a really good way of just motivating a team, because you feel progress as a team as you're lowering this, as you're kind of working towards this metric. But the other thing that it really provides is clear focus. It lets you prioritize hypotheses. As you're doing your research, you will kind of find a lot of really interesting things along the way. And it's kind of really easy to get into this this mode where like you just like find something really, really interesting, and then you just go down a rabbit hole. And this is where metrics help, because you can always ask yourself, do you really think that this will help optimizing towards the metrics? So it really helps a team prioritize and like discuss in a very objective way the tasks and hypotheses that you have. So for productivity in general, like spending the time at the beginning of projects to pick your data sets and pick your metrics is at least what I found, it always pays off. So never never neglect this one. Any questions on the metrics? Okay, third thing. When I talk about, which is kind of most related to the stuff that Josh was talking about, is tooling. And this is also one of those things which is often relatively neglected. By the way, could I have something to drink? My throat is itching a little bit. Okay, thank you. So in order to kind of traverse this jungle, you need a really good set of tools. And often when you start out, you don't know what those tools are. And you're building those tools along the way. You're trying to kind of figure out what are the things that are going to make me move fast as quickly as possible. Again, like it looks like you kind of have to get. Thank you very much. You have to get through something like this. So that's really hard, and kind of thinking about the tools is a worthwhile thing to do. Now, as you're making progress on your hypothesis, some things will not work out, and as we discussed, like you might have to throw away code. But whenever things do work out, it's kind of worth the effort to kind of make it into something solid that your teammates can use, because kind of to get through this, you want to turn like the thing that you had in your experiment into something that's like super useful. Like you want to turn your stone axe into a chainsaw so you can really get through any problem that you have along the way. And that means that once you have figured out once you have validated, or even in some cases invalidated your hypothesis, you kind of need to move your science to engineering. And this is where we can use all those best practices that people have developed in engineering for a really long time, like code reviews, integration tests, unit tests, thoughtful interfaces. And these things are all really important. Integration tests, I would argue, is probably one of the most important things. As Josh said, like we've had this, if you don't have them, what happens, and I've seen this happen in many settings, many times at Dropbox, many times at OpenAI, is at some point you have a regression, and you didn't know when it happened. And you have to kind of do a binary search back in your commits, and your data sets might have changed and stuff. It's just like usually a big nightmare. And almost every time this happens, you can spend anywhere from like a week to a month trying to figure out. I remember there was a famous example of this at Google, where one of their Google Nets or something like that basically regressed, and it took like a team of 5 people a month to find it. Like this happens to the best of us. So it kind of pays off to set up really good processes around tracking, making sure you don't break things along the way. I think another thing that's really important is actually thoughtful interfaces. This is something that's even more neglected, but it's extremely important as you work as a team, because everybody are going to work on your code. So at OpenAI, we try, I wouldn't argue we're the best at this, but we try to spend a lot of time like thinking about our interfaces, commenting on it, like adding a lot of documentations along the way. Very simple things that I think are really important are things like if you have a model, being able to very easily load that model, run a prediction with it, and so on. Like you would be surprised the amount of time I've seen just a whole lot of boilerplate code in order to even like run a model. And what that usually results in is just lots of bugs and like assumptions. If you should try to kind of encapsulate as many assumptions you have as a team into really useful and easy to use interfaces, because that way you can move much faster. You don't have to think as much about the things you do, and all of those conventions that each person has developed individually, they become kind of codified in the actual code. Also, as Josh said, like at OpenAI, we have a lot of tests. We have like every one of these folders have additional lots of tests. Like it's just well worth it. Like we try to have a pretty hard policy around whenever you add new code, you should make sure that it's tested and also potentially test some of the old code. And we found that this has just made us move much faster. And it's one of those things where you don't do it much if you're doing individual research, because often you have a lot of context on the code and you don't maybe have the time to do it because you have a paper deadline or something like that. But as a team, it's like so important, because you need to make sure that interfaces don't break. You need to make sure that you can load old models and stuff like that. Like it's something that, and it's also a way of kind of documenting even the way that your code works. So as a team, it's like even more important. Go ahead.
So as far as I understand, you're accumulating more and more tasks as you go, and given that you have this hypothesis model, you're battling something. So very quickly, your tasks turn into the liability that you need to maintain. You need to grow them. You probably have some set of best practices on that. Could you share those?
Yeah, sure. That's actually a really good question. We actually try to delete a lot of code as well. If we find that we don't use some code, we're pretty brutal in deleting it. like just knowing that we can always find it back in our Git history if we ever needed it again, it's usually not worth keeping around things that we don't use because they're just going to hold us back. So we do that. We also try to take the time every now and then to refactor and rethink what we have done and put it in a much better framework. This is often a hard thing, but it is also often worth it. Especially, like a place where this often happens is if we have one direction and the code is not super nice, it's usually good to refactor it before more people come on board. Just because then, that's just gonna make it easier for people to collaborate, like modularize things, make things less coupled and stuff like that.
Does that mean that your refactoring is happening before you do the next set of hypotheses?
Yes, that happens. Like before, like we would just block on new hypothesis for a while, and it's usually well worth the effort.
How far do you take the engineering analogy? Like you have style guidelines and typing and...
Yeah, we actually try to have a lot of that. We have we have linters and stuff for our code reviews. Like again, like just to make it very easy to read the code, because like the truth with machine learning code is that like bugs are usually extremely subtle. It's extremely easy to have bugs, and when you have bugs, you might not even know about it because it's just like your model isn't learning as good as it should be learning. It's like it's still learning, but it could be learning better. Like that happens all the time. So making code extremely clear and easy to see what's going on. Like one kind of pet peeve I have for a lot of like implementations of machine learning algorithms is that they have all A, alpha, beta, all these things, and they make no sense. And usually there's pretty good name that you can apply to it. Like you can name it something like learning rate or like discount factor or something like that. And then the code becomes much clearer. And we try to apply a lot of that to our code to just make it readable, because that's actually the best way to avoid these bugs.
And then you get complaints from researchers who are now forced to follow these very strict guidelines.
I don't think so. I think because like often, and I think Josh alluded to this, like in the beginning when you try out a new hypothesis, we're not so strict with this. Like if you're just trying something out, like it's actually better for you to move quickly and just try out a lot of things. It's more like when you want to merge it into kind of master or like get other people to use it, that's when it's really, really important to have something that's really reliable and well formatted and stuff like that. Because when you're at that validate or invalidate hypothesis stage, like more likely than not, you will throw away your code anyway. Let's see. I will just move quickly through the other slides because I think I'm running out of time. The fourth thing I want to spend just a quick amount of time talking about is building out the map. And this is like alluding to the question I got before, is kind of how do you kind of build up a sense of what you have learned so far? And you might know that there are kind of dragons hiding behind a tree or something like, and you don't want to go back to that dragon. And so you need kind of really good processes if you're a large set of people to learn from each other and spread that knowledge and kind of build up the map together. And I think there's some very simple things to do. There's lots of tooling around this, but like you should like not forget the very simplest things. Like for example, one thing we do a lot at OpenAI is like for every hypothesis, we try to write up a little bit of a document. Like what is this hypothesis? And and then like have a little bit of a logbook of the experiments that were being run and the conclusions of those experiments, so that we use Google Drive a lot for this because it's just very useful for people can comment on it and so on. So as you're making progress on your experiments, you post your experiment log and your results in a Slack channel as well. You get feedback on that. And it's really useful to go back, like, oh, how was that experiment going? Like, why did we make that choice like 2 months back? It's really good to have this very explicitly. And so we try to be relatively strict on this. Like, I think it's one of those things we tried different formats of doing this, and then at some point the simplest way was just to write these Google documents, and then once we removed a lot of the process around it, people just started doing it. It's like the way to think about it is it's just your little logbook for your hypothesis, and the only thing you should be very clear about is what is the hypothesis you're trying to prove or disprove. Make it very, very clear. Now, the good thing is that there are a lot of cool tools. I mean, there's weights and biases. They're not paying me for saying this, but we have been using it a lot at OpenAI. And it's really useful because you can go back now. Often people link to the weights and biases experiments in these logbooks, so you can actually go back and look at the logs, so you can download the models and these things. It's actually helped us quite a bit. Our workflow for this before was pretty terrible. So I'm very happy this tooling exists. But then there are other things that are very, kind of simple, but we still do, like we just use this Google spreadsheet. And here's like, we put in how we're doing at a core metric. We have links to weights and biases, some notes about the things that we were trying. And we just try to be very transparent of what we're doing in a team and like logging all the results in one place. And like, again, very simple tools, like a spreadsheet, a Google Doc. It's very simple, but it helps so much in terms of understanding how you're doing and seeing how you're making progress. So it's just using these tools to build up the map along the way lets you learn as a team and just become and the risk you run otherwise is that people have context of the little hypothesis, but nobody else, and then you can keep on redoing the same mistakes over and over again. And that's kind of what you want to avoid. Any questions on that?
In your logbook, is there like some strict rules about like it should be, penned only like a scientific journal?
Not at all. We have very little rules about it. It's mostly like put all the stuff that you're thinking about in there, and then like usually, again, like if you put, I kind of feel like if you put too much process around it, like it becomes too cumbersome. You kind of want to let, and every person have a slightly different workflow. Instead, if I go into a logbook of somebody else and I don't understand something, I add a comment and ask them about that, and they add that content. So we try to make it very agile in some sense.
Do you have like a in-person or a Slack stand-up kind of situation to discuss some of these?
We usually have, for some of the projects, we have like weekly kind of meetings where we discuss some of these. A lot of it happens on Slack. I would say like 90% of those discussions happen on Slack, and then, then they kind of migrate into in-person discussions if it's so needed.
And then if someone finds a breakthrough which stops other people or like has to shift other people's work, what does that process look like?
I think that's the case where we just like, we take, if that happens, it usually becomes very clear very quickly to everyone. And like people feel like, why am I even working on this when this breakthrough happened? It's not like somebody discovers it in secret and we need to tell the whole team kind of. So it happens pretty organically, like either immediately if it's super obvious or like at the next meeting we just like need to replan. The last thing real quick is, actually the most important I think is, if you're doing research, you really need to kind of nurture your creativity. Like, I feel like engineering requires a lot of creativity, but for research, it's like you're really trying to do things that nobody has been able to do before. And there's usually, for a lot of things, it's kind of very unclear what's the right path. So you need to kind of really be creative along the way. And I think this is something we kind of realize more and more, the importance of at OpenAI. You kind of need time to play. And if you structure your work a lot to make progress, like I was talking about here, it's very easy to get into mode where you just like optimize your milestone all the time and you don't have time to really take a big picture and like think, are there completely different ways we could be doing this? So, but since this is such an important part of research, you kind of need to formalize it so that you really give people the space to be creative and learn new things. So one way we've done this at OpenAI that turned out to be very successful is that we have a weekly learning day. So every Thursday, this sign lights up in the office, and that day, everybody should be learning. And we take this extremely seriously. You shouldn't do any other work on this day. You should be learning, only learning. So we set up like a set of rules for it. It's just 1 day per week. If you don't use it, you lose it. So you're not allowed to kind of have them roll over for multiple weeks and so on. Like you need to be learning every week. It must be related to work. So like if you want to learn skydiving, that's not really what we want it for. Like it needs to be it's really to make you do your work better. But that doesn't mean that it has to be directly applied to the problem you're working on at the time. It could be like, I feel like I'm rusty on my calculus foundation. Then that's something you might be learning that day. Because we believe if you spend the time to build the foundations, you will be able to just accelerate as a person. So a lot of people spend time on that. You basically spend the time reading papers or books, you implement things, you experiment with new ideas. This is kind of the time we give people to really do that. But then the kind of most important things here is like, you kind of need to share what you've learned. So if you're doing an experiment, like trying out some new idea, you need to tell people about it. So we have a Slack channel where we talk about this. If you read a paper, you summarize it. If you implement something, you talk about the experience you had implementing it. And we hold people accountable to this. So you kind of have to say, like, what am I learning this day? And I think this is really important because it means, like, if we have somebody who is really good in reinforcement learning and they say, like, well, today I'm actually reviewing a very basic text on reinforcement learning, that kind of removes the stigma of going back and learning the foundations. And if you see that everybody else are doing this, so you feel like it's OK to learn anything I want to do that I think believe kind of makes my work better. And so throughout the day, you kind of need to update this channel about, like, what have I learned so far? And, like, am I changing? Like, maybe I'm bored of reading papers now. I'm going to do a bit of implementation. You actually have to say that. And the other part of this is, like, if somebody is not learning something, maybe they're, like, working on something that, like, and that's not a good thing. They should be learning that day. Like it's just as important as the rest of their job is the learning part, because that's how we all, like, just become better and level up. And so far, we found that it's just paid off huge dividends. Like, people are able to kind of just be much faster at implementing things because they spent learning day just learning new frameworks or learning new machine learning concepts. Like, overall, it's just a really good way for people to accelerate what they're doing, and it's been totally worth it. So if you're not doing something like this formally, I really encourage you to, because you're just going to be so much better as a team. And that's pretty much it. Just to summarize these 5 things. Think about hypotheses and not tasks. Find a metric that you're optimizing as a team. Spend the time to improve your tooling and document your progress and to build out the map. And then, last but not least, nurture that creativity so you can actually make progress. That's it for me. Thank you.
I know this is sort of hard to quantify, but I'm curious, like, what you found is the right balance between, like, diligently pursuing, tasks and experiments versus, like, just sort of blue sky, trying things you haven't thought of before.
So we try to pretty relentlessly do the first thing, and then we leave the learning day for the second thing. So if you have, like, really blue sky things that are somewhat related to what you're doing, that, like, the learning day would be a really good time to do that. I think one philosophy that we have is, as you're making progress on your problem, you will find a lot of, like, what the open questions are, and you will get ideas towards that. So you don't necessarily need a lot of the really blue sky things. And I think this is also the difference from, like, say, the way we approach research from a lot of academia is that we just, like, this is the more blue sky stuff is what a lot of academia is doing. It's really good. It's not at all clear that we would be better at academia than that. So we take a more kind of goal-oriented and engineering-oriented way to approach research, because we think we can just, it's much easier for us to do that than in an academic lab, for example. So it's just a different kind of philosophy for us. Does that make sense?
What is the process of multi-A learning projects?
Right now, we have no process for that, basically. Like, I think the idea for that is, like, if you're really passionate about it, like, you're probably going to work, like, nights and weekends on that kind of stuff. Sometimes we have, like, hack weeks. Sometimes if we feel like it's a really, like, often, like, people use learning day to kind of validate, do some simple experiments to validate an approach. And if it seems to really align with the project, then that becomes a new hypothesis or something that might work.
Great.
Okay.
Let's
Okay.
actually wrap up here. Thanks again, Peter.
Thank you.